では、アレックス・ラトナー先生のご紹介をいたします。アレックス・ラトナー先生は、シュノーケル AI の CEO であらせられまして、また、ワシントン大学のアシスタントプロフェッサーでもおられます。で、2019年にスタンフォードにて博士号を取得された、だいぶお若い先生です。はい、で、博士課程の在籍中に、機械学習分野で、最近ちょっとトレンドになっているウィークスーパービジョン、弱教師あり学習といわれる、分野があるんですが、その一つとして、訓練データをプログラムを使って半自動的に構築する、後に、データプログラミングと呼ばれるようになる手法を開拓されました。で、この手法を実装したオープンソースのライブラリ、シュノーケルを開発し、それによって、大規模な AI アプリケーションの開発期間を大幅に短縮させることに、成功ということで、このライブラリがGoogle や Apple、Intel、他多数の大学の研究室、政府機関にて採用された後、このライブラリの商用バージョンを開発するシュノーケル AI という会社を同僚の方と創業されました。で、その後、ワシントン大学でのポストにも就任され、機械学習より実用的にするためのシステムや技術に興味を持って、研究に勤しまれているということです。では、始めていただこうかと思います。So Alex, please go ahead. just a moment, please. ごめんなさい。で、質問は、Zoom の挙手の機能を使って、挙手してください。で、ただ英語ですので、どうしても難しいという方は、チャットか、スラックの、キーノートのチャンネルで、テキストで質問していただければ、もし口頭での質問がなくなったら、そちらを拾うかもしれません。口頭での質問を優先しようと思います。はい。Okay. So Alex, could you start, please?
Yes. Hey, can you hear me?
Yes.
Great. And can I go ahead and share my screen?
Yes. Okay. So could you share?
Yes. Great. Can you see my slides?
Yes.
Perfect. So first of all, thank you so much for the invitation to come speak here and interact with you all. I'm greatly appreciative. I'm embarrassed because that already seemed like a long introduction, but you all have been too kind to introduce me, and I'm excited to get to walk through some of the specifics and also broad details of what we've been working on both at Stanford, at UW, and also at the company that we spun out of Stanford around some of this work called Snorkel, and hopefully have some discussion. So please jump in on the chat. I'll leave some time for discussion at the end, and I'll pause in between sections, but also feel free to just, I don't think this is too big of a group to say this, so I think, please just jump in, and I can't see everyone's faces, but if you just start speaking, I'll pause and would love to take questions or comments. Also, I'll watch the chat. So I'm very happy to, in fact, even more happy to have discussion during the talk. Otherwise, I'll leave time at the end if there are questions. Also, if I'm speaking too quickly or anything, please tell me to slow down. I would try. I once learned a little bit of Japanese. I would try, but then I think I would give you a very poor talk. So I'll proceed in English, and if you want me to pause, slow down, repeat anything, let me know. Okay, so today I'm going to talk about some of the broad work, both academic and also out deployed with large enterprises around what we think of as data-centric development in AI, in contrast to model-centric or other kind of development loops, and also this idea of programmatic or weak supervision as a way to actually do data-centric AI. Okay, so let me jump into this. So a lot of the work that we've done has focused on this perspective of what is slowing down development of machine learning or AI capabilities more broadly. And circa 2016, when we started some of this work, we were looking at some of these big shifts occurring in the space, and we were seeing that some of the bottlenecks, some of the places where people were getting stuck and having pain and slowdowns and difficulties actually deploying and developing ML was shifting in a pretty interesting way. And so for this talk, I'm going to largely focus on supervised learning. So this is, imagine you're taking in a document and you want to use machine learning to classify what type of document it is, or pull clauses or facts out of it, or triage a medical image, etc. Supervised learning is where you start with a data set that has been labeled with the correct answer, and then you train a machine learning model to make that prediction or output that answer for new unlabeled data. So there are three main ingredients at a very high level. There's the training data, this data that's been labeled with the correct label or tag or outcome or action that you want the model to produce on new data. You have the actual model, which is the function or the box that you're trying to train or teach on this data that you can actually then deploy in production to make new predictions or produce new outputs. And then you have, and this is a very broad bucket, just for the sake of simplifying the talk, all the infrastructure. So this includes everything I'm bucketing together from the algorithms that train this model to all of the layers of the stack that support both training and serving or inference time. So it used to be that 5-10 years ago, that if you went to you picked a random ML team that was trying to get models deployed, you asked, what is your biggest pain point? Where are you spending all of your development time? You'd probably get an answer around the model or the infrastructure, right? So a lot of the work out in the real world, as well as in the research world, were around things like developing better model architectures that were fit for certain tasks, whether it be image classification or text sequence tagging or time series prediction, et cetera. Doing what's often called feature engineering. So trying to pick out the specific aspects or features or attributes of the data and transform them so the model could then look at them and make predictions. Designing new algorithms for scalably training this model, building all the infrastructure to then train and serve these models. And again, you talk to a random group, they'd probably be stuck on these things: feature engineering, model development, all of this type of stuff. Fast forward to today, for many what actually used to be grand challenge tasks, especially a lot of the work that myself and colleagues have done is over unstructured data like text, image, video, time series, et cetera. Things that are traditionally quite challenging in machine learning. A lot of the state-of-the-art models and algorithms and infrastructure approaches are increasingly just a couple lines of code to get running. So, increasingly the models, the algorithms, the infrastructure are increasingly not just more powerful and more push button, but also increasingly commoditized and accessible. And I mean commoditized in only the best way in terms of increasing accessibility. But there's usually no such thing as a free lunch. And so what happened in return? Well, we got these models that literally you can get state-of-the-art in a couple lines of code. You don't need to do any feature engineering. You don't need to do lots of custom tuning. You just take a very standard architecture and you throw it at a blob of text, and it learns to classify it, or ditto with images, and increasingly well-supported, accessible ways. A lot of these models are what are referred to as deep learning or representation learning models. But at a very high level, in return, the trade-off is that these models have orders of magnitude more parameters. They're much more data hungry. They need much more labeled training data to be trained to get a reasonable performance. So essentially what's happened over the last 5 years, again, just at a very big picture level, is that a lot of the practical pain points and bottlenecks and costs of actually developing and deploying machine learning have shifted from the model and the infrastructure, which are increasingly accessible and commoditized either in the open source or in fairly commodity commercial solutions, or but actually the pain points have shifted to the training data. rather than having a couple hundred or a couple thousand examples that you quickly label, and then you're on your way to dealing with the model and infrastructure. Now you often need hundreds of thousands to millions of labeled data points for every single modeling task you want to tackle. So in many scenarios today, especially with more complex data types and machine learning task types, the volume, the quality, the approach to managing the training data, the labeled training data, is really what differentiates success from failure and what blocks projects from actually getting deployed, rather than the model or the infrastructure. So let me give an example of just one emblematic example from some of the work that myself and colleagues have done. This is from a line of work still ongoing with the Stanford Radiology Department and Stanford Healthcare System, as well as the VA healthcare system, most recently published in Radiology and also Cell Patterns. And in this case, I won't go into the details because not the main point of the talk. You can see the papers for more, but basically we were tackling a bunch of classification or triage or medical monitoring problems. So there were a set of them over various different medical modalities. But to give one example, imagine you have a chest X-ray that comes into the hospital, and you just want to classify it as requiring urgent attention from a doctor or not. So these are human assist, not replacement tasks, or otherwise known as triaging. But really, it just comes down to binary classification. Image comes in, you want to classify, one of two severities. And so this used to be a problem that many entire PhD theses were devoted to, just building the right model, the right features, the right architecture, the right algorithms to try to get some reasonable performance at a task like this over a complex data modality like a radiograph. This is actually about a year and a half, 2 years ago. Our collaborators, who weren't even machine learning experts, they were in the radiology department, basically took them a day or two to train state-of-the-art models that got within human performance at this triaging task. And if you compared the best model at the time with the second best, with the third best, and so on the leaderboards of state-of-the-art models, there was about less than a point of difference. This was ROC AUC, but you could just think of it's an accuracy equivalent metric. Point is, very quick, and just to download some of these from the internet, a couple lines of code, get them trained up, and pretty small variance between the top models. In contrast, it had taken 8 to 14 person months across the applications we surveyed to actually label the training data to get to this performance. Had to have a Stanford radiologist sitting there for 8 to 14 person months, just clicking, labeling these chest X-rays to actually label the hundreds of thousands of data points we needed to get those performances. And the difference between a few days or weeks of that labeling and the full amount of labels, and also the quality of the labels, was 10x or greater than the difference between which model you used. So again, this is just to highlight, obviously the models and all parts of the pipeline extremely important here, but often the models are in some sense the easy part, and the part that's tough and that you get the biggest differentiation around, whether it be in real world settings or even if you look at a lot of the kind of academic benchmarks these days, is around the data, how you label it, how you clean it, how you manage it, how you partition it, how you augment it, etc. So all of this is to kind of point to this, this centricity, this focal point being on the data. And it's worth just double clicking a little bit here and saying that a lot of where ML progress has been broadcast around are problems where data is either already implicitly labeled. So think about a problem like you often see commercially, customer churn prediction. Has a customer quit using your service or not? Well, you have the labels for that. You gather them implicitly just by running your service. So you have labels already. Or settings where it's very cheap to get outsourced labeling. So is this a cat or a dog? Or is this a pedestrian or a stop sign for self-driving? These are use cases with data that's fairly public. It doesn't require specially trained subject matter experts to label. It doesn't change that often. Cats and dogs and stop signs and pedestrians don't change that often. So you can basically ship this out off-prem to some people to label by hand for pennies on the dollar, send back, and you at least get a serviceable solution. And many of the big tech companies in certain areas like self-driving are spending hundreds of millions to billions of dollars, or have spent this much money doing this manual labeling. But most of the world, and these are the users that we worked with on the academic side, customers that we work with through the Snorkel company now, including 2 of the top 3 US banks and government agencies and large global enterprises, often have settings that are much, much more difficult than, is this a cat or a dog? You have data that's highly private, so it's very hard to ship it to someone to label. You have data that requires subject matter experts like doctors or lawyers or government analysts or technicians or underwriters, the list goes on. And you have data that's changing constantly. The data distribution coming in is may be changing. The upstream pre-processing might be changing. The downstream post-processing or consumption, the schema or the set of labels that you actually want to predict might be changing. And all of these things make the practice of just labeling data by hand just very untenable, even for the world's largest organizations. So we did some deployments that we published about with Google that are in some of their core systems that make a lion's share of their revenue, had a massive impact on that. Even with all of that money and resourcing, still couldn't have people manually label data fast enough to keep up with changing real world conditions. Give another example, again, that radiology setting took 8 to 14 person months. And we went to another hospital system and they needed a slightly different label schema. They needed 5 severity classes rather than 2. So we had to relabel everything from scratch, or would have if we didn't have a different solution. So again, we have this reality in many, many use cases, many settings, where labeling and managing this training data is really the key blocker and the key leverage point. And you really can't just deal with it by asking some people to label it by hand. It's just not a feasible solution, even for the most well-resourced organizations in the world. So we have this reality where literal billions of dollars of investment across industry and government and nonprofits in teams and tooling, et cetera, are just blocked waiting to get data labeled. And another spin on this, and this goes to my title slide and some of the recent verbiage that's been out there around data-centric AI is just this point that you end up spending all of your time and you get the biggest impact from spending your time on the data. The data is the center of your workflow, this labeled training data. And to actually handle this, you can't just rely on the old method of asking some people off, somewhere else to label it by hand. You have to have, as data centric, as AI becomes really data centric in terms of what you're working on, you need to come up with new tools and new processes for doing that kind of data-centric AI. So one approach that I'm going to talk about now in more depth is this idea of what's often called weak or programmatic supervision, programmatic labeling. And it's actually, as we'll get to if we have time at the end, about a lot more than just labeling. This includes work that we and others have done on slicing and augmenting and partitioning and otherwise managing your data. But I'm going to start by talking about one of the core operations in supervised learning, which is labeling this training data. And the key idea at a high level is a very simple one. It's just labeling data by using programs rather than by hand. So trying to raise the abstraction level by which you not just label this data, but really interact with and effectively program your machine learning models. And so again, this might look like asking the radiologist to heuristically identify some features of the image or some words in the report for the chest X-ray, rather than just clicking one by one to label data. And the hope is that by labeling data programmatically, we can make these person months of labeling time go into hours of something that looks more like any other kind of software development, so that AI can actually be practical and not blocked on the data. Okay, so let me just, that's a little bit of the prelude and the motivation. Let me just pause there and see if there are any questions or comments.
May I?
Yes, yeah.
So it's going to be a very naive question, but since the purpose of machine learning is to determine whether this data falls into this category. So if you can programmatically label, then why do you need to do machine learning?
It's a not at all a naive question. It's a great one, right? And so we'll get into this and I'll circle back to it a little bit more later in depth, but the short answer is that the goal here is to label some data at some level of precision or accuracy in order to train a model that can label all of the data at very high accuracy. So it's kind of like a form of bootstrapping. And it's not dissimilar, again, when you manually label data, you're manually labeling some amount of data, and then you're hoping that your machine learning model will successfully generalize to all of the data or all of the data within some distribution that'll come its way. Similar idea here in programmatic labeling, or same basic idea. If we can have people programmatically or heuristically label some of the data, some percentage of the data with some accuracy, as we've shown in our work, and I'll kind of outline today, we can use that to train a model that covers 100% of the data and new data as well with greater accuracy.
Okay, I think.
And even that, sorry, does that make sense?
Yes.
Yeah, and even that, you know, that shouldn't be a claim that you take immediately. You know, proving that can be done both theoretically and practically is a lot of what the work went into here. And so I'll outline at least a little bit of that high level, but it's a great question. One other thing, since you brought it up, that I think is worth mentioning here is that, and we can talk about this more later, but you know, there were a couple of principles that went into the design of this approach from a systems perspective and from a practical perspective. And one of our goals was actually to provide a pipeline where if a very high-powered machine learning model was not necessary, we didn't waste the time training it. So one thing, and this is a little bit of a broader note, but one thing that you often see in the space, I know I've seen it many times, I'm sure many of you have, is people throwing very large, fancy, you know, powerful models at problems that don't need that, you know, that kind of a model or even any machine learning at all. And the problem is that you don't always know whether you need the fancy model before you spend a huge amount of labeling and compute resources to train it. One thing that we wanted to do, practically speaking, with this programmatic and Snorkel approaches I'll get into, is to allow people to write some of what we call these labeling functions. And if it actually is good enough, you can just programmatically label 100% of the data at 100% accuracy, stop there, and don't use a further machine learning model, right? That's actually a great practical outcome from our perspective, because we've just saved some, you know, users time from having to, you know, train some massive deep learning model overnight. Whereas if you take the hand labeling approach, you don't know in advance. You spend maybe months labeling data before later you figure out, hey, I could have just written a couple of heuristics and been fine. So that's actually another big motivation, even though I often talk about that less, but that actually was and is one of the big practical motivations. If that makes sense too.
Thank you very much.
But great question. We'll come back to it. And actually, the last thing I'll say is that there's actually still ongoing work about kind of sharpening our theoretical bounds about these generalization properties. In other words, if you label 20% of the data with these programmatic approaches, in other words, you label a biased subset, how can we sharpen the theory around, you know, guaranteeing when and how a machine learning model will generalize to the other 80% of the data? That's still somewhere where we still have work on the theory side, but lots of great empirical as well as, you know, theory evidence of how that transpires. Anyway, as you could probably tell from my outpouring of chatter on this, it's an awesome question. But I think again, the very short summary is the goal here is to programmatically label some of the data, just like with hand labeling, and train a model that can be deployed to make predictions on all of the data with higher, not just coverage, but precision too. Okay, awesome stuff. So moving on, the other broader idea, and I'm going to use this programmatic labeling paradigm and a system built around it called Snorkel Flow, to really just, you know, I'm going to go into depth about them and that specific paradigm we were just even talking about, but I'm also just using it to, you know, illustrate a broader shift and trend, like I mentioned before, from, you know, model-centric development workflows and systems and principles, where your primary activity is developing features of the model or model architectures or hyperparameter tuning, et cetera, to where your most important activity is developing your data, labeling and managing your data. And programmatic supervision and the system I'm about to describe is one way of doing it. But I think it's worth highlighting that this is part of a broader trend, in our opinion, towards data-centric AI development. And so that's the other thing that I'm going to emphasize here, is about how this isn't just an algorithmic trick. This is a new development process. So you don't just label data programmatically once and then you're done. It's all about a new way of iterating and iteratively developing that centers around your data. So to talk about this, I'll use a high-level description of a platform called Snorkel. And Snorkel is a current commercial platform for a company that I'm CEO of, that we spun out of Stanford. And it's based on a Snorkel research project where we've published a number of papers, I think over 50 at this point, around a lot of the core principles and ideas. And so you can find all of that gory detail online if you're curious. But I'm just going to use this as an illustration of this idea of data-centric and programmatic AI. So the key idea in Snorkel is, again, really about a different kind of workflow, where your focus is on rapidly and iteratively developing and labeling and managing your training data. So the first step is this idea of writing what we call labeling functions to label data programmatically, as well as other operators that we'll talk about more at the end of the session if we have time. And then automatically cleaning and modeling their outputs, using these to train models, and then analyzing where there are mistakes in the model to go back and iterate. And the goal here at a very practical level is to turn machine learning development into this process where 80 to 90% of the time often is just spent labeling data or waiting for some relevant experts to label the data before you can even train a model. And then when something changes or something is not good enough, having to go and relabel all of that data all over again. In taking that process into something that looks more like any other type of software development, where you sit down, you write some code, or you push some buttons through a no-code UI, you compile it, in this case, train a model, you debug, and you iterate. And you iterate a bunch of times in an afternoon, and then you have an output that works, right? So that is the goal that all of this is aimed towards, and that we've seen in practice with many users over time. Okay, so the first idea here is this idea of writing what we call a labeling function. So imagine, we'll switch examples here. You're trying to, let's say, classify a contract. Is this contract type A or type B or type C? This is a simplified example of use cases that are running in practice at major U.S. banks and global companies on top of Snorkel, for example, and that we've also published about on the academic side in the scientific literature. But really simple example of a labeling function might be saying, look for the word credit in the title, or what I think the title might be. If so, label the credit agreement, otherwise abstain. And really, that's the only kind of semantically interesting part of this labeling function definition, the fact that it can abstain. Otherwise, it's pretty open. The goal is to have this be an abstraction that admits any kind of and many kinds of input. Or again, really the only interesting thing is that it does have an ability to abstain. So there is a notion of how much data is covered by this labeling function. It'll only label some small portion of the data set in general. Now, these labeling functions can be used as an abstraction for all types of signal, what we often call weak supervision. Weak meaning we don't trust that it's 100% accurate or covers 100% of the data. It's just some kind of usable signal. And we can define that more later. So these labeling functions could abstract away pattern matchers. They could abstract away Boolean logic, cross checks against databases or knowledge bases or ontologies, heuristics, legacy systems, other machine learning models, labeled data too, especially if it's from untrusted sources like crowd workers. And basically all of these things can be abstracted as a labeling function and dumped into Snorkel. This can be in a platform like Snorkel done either via a point and click no code UI interface or through a Python SDK. And a lot of the motivation behind this design was, on the one hand, allowing complete expressivity for a developer. There's an increasingly large group of folks who, even if they might not be machine learning experts, can write Python code and can import libraries and data sources and other usable pieces of signal in via Python scripts. And we want to make sure that they have complete expressivity and flexibility to be creative and dump in this weak supervision signal. But also, actually one of the earliest sources of funding for this whole research project was around the idea of trying to get the subject matter expert who potentially doesn't write code more into the loop, rather than just having machine learning developers over here and subject matter experts labeling training data by hand over here and having a wall between them where the only communication is through these kind of labeled XY tuples and nothing else. The idea is to put the data scientist or machine learning engineer and the subject matter expert who knows how to label the data in the loop collaboratively. So letting them actually write these labeling functions is a big part of that, even without writing code. Okay, so let's say you've written some of these labeling functions or you've developed them by pushing some buttons. We've also had research over the years from some of my colleagues on even higher level interfaces like natural language interfaces where you explain how to label a data point. This gets semantically parsed into a labeling function, where we've used eye trackers to look at where people are looking, say in radiographs, and using that to compile labeling functions. So I'll note that going from manual labeling to programmatic labeling is just the first step. It's like going from zero and ones and zeros to assembly language, and then on top of that, you can build all these other interfaces and abstraction layers to make it even faster and more efficient. But okay, let's say you've programmatically labeled all this data. Benefit of this should be obvious. You can label data in a fraction of the time. In that radiology example, for example, as one example, we went from 8 to 14 person months to about 8 hours on average of just writing these labeling functions to get to the same quality level, or I think it was within 1 point of the score. So literally replacing months to years of person time with a couple of hours of writing these labeling functions. And it's all the other things that come out of this shift from manual labeling to code that matter so much in practice. The ability to audit and have governance, the ability to label privately without having human eyes on the bulk of the data, the ability to change and reuse and modify over time, because it's now as simple as just going back and modifying some code if you want to change your training data set and your model, versus having to do what even some of the largest companies in the world, like in the paper we published with Google, do, which is throw out the data and start all over again. But what's the trade-off, right? I said earlier in the talk that there's no such thing as a free lunch. What's the trade-off here? Well, the trade-off, or rather the challenge, is that these labeling functions are what we often call weak or noisy supervision. In general, can't really assume that they're going to be 100% accurate. So they may, they may be inaccurate. They're generally not going to cover all the data. They're going to abstain on a lot of it. They may be correlated in that they are conditionally correlated, to be more precise, and that they actually might be kind of redundant, and you don't want to double count them. They might have biases in terms of where they're actually accurate. Maybe one labeling function is really accurate in the daytime, but really inaccurate for nighttime data, et cetera. And all of these challenges, we often refer to as this problem of modeling weak supervision. And I won't go into a ton of detail here, but a lot of our work is built on very old theoretical intuitions and work on this idea of looking at the agreement and disagreement patterns between these labeling functions in order to estimate their accuracies, correlations, expertise areas, et cetera, even in the absence of ground truth with theoretical guarantees. So just to pause here for half a second, imagine that everyone in this virtual room today had some kind of base accuracy rate, just to take the simple version of the problem. Some of you were telling the truth 90% of the time. Some of you actually maybe are lying 90% of the time. Imagine I get to ask you lots of questions, yes, no questions, but I never see the true ground truth answer. As long as, under this simple model, as long as there are at least 3 sort of independent groups of you that are not colluding, so as long as everyone is not colluding, there are at least 3 independent clusters, then I can provably recover everyone's accuracies if I get to ask you enough yes or no questions, even without ever knowing the correct answers to those yes, no questions. And the intuition is kind of a simple and old one, which is that, if I look and I see that, someone is tending to agree with everyone else when they label, I'll trust them a bit more. If I see that someone is tending to disagree with everyone, I'll trust them a little bit less. If 2 people are always giving the right, the same answer more than you'd expect, I might model them as correlated. And given those basic assumptions that there are not too many correlations, there's enough degrees of independence, and given lots of yes, no questions, I could provably recover your accuracies and intuitions, or your accuracies and other parameters of this weak supervision modeling problem. So again, I'm holding back from going into too much gory detail there, but the basic idea is that. And some of the specific ways that we've instantiated this include one that I have a little picture of here, which is using the inverse form of the what's called generalized covariance matrix in a kind of matrix completion style approach to provably recover these parameters. There are other things based on Gibbs sampling and stochastic gradient descent and more algebraic methods, but the basic idea is the same intuition. Without separate ground truth, we can look at the agreements and disagreements, the overlaps in these labeling functions, and provably pull out which ones to trust and trust more or less, or weight, up or down weight accordingly. Okay, so that was all a mouthful. I just wanted to give a little bit of technical, in the weeds stuff for those that are interested in that kind of thing. But pulling back up, the high level idea here is that we can take in, these labeling functions, these weak supervision sources that have to be somewhat reasonable. The basic assumption that we actually make, the other one that you need to break some fundamental theoretical symmetries, is that more of the labeling functions are trustworthy than are bad or adversarial. So basically, what this translates to in practice is that if you write a reasonably accurate but far from perfect set of labeling functions, we can clean that up and integrate them into a final clean set of training labels, without you having to manually make them all perfect or make them cover all the data or adjudicate between disagreements, et cetera. You just dump them in, and better labeling functions will lead to better outcomes in general, but they don't have to be perfect by any means. Maybe there's a bunch of them that cover 20–30% of the data in aggregate, are 60 to 70% accurate on average, and Snorkel will take care of the rest, and we'll kind of clean and merge them into a final set of labels. A lot of this integration also has to do with auditing and management. Now you can now go back and you can see which of these labeling functions and weak supervision sources are trustworthy, which have problems and should maybe be corrected or removed, et cetera. Okay, so now we've programmatically labeled some data. We've cleaned up that messy programmatic labeling. We can use it to train large data-hungry models. And then most importantly, we can now close the loop and actually inspect for errors and then go back and correct them in the data when they're present. Right. So a lot of ML deployments in practice get stuck on, the model is making some error because the data is flawed or because something in the world changed and the data is stale and no longer relevant. What do? I mean, with hand labeled data, going back and fixing that data is theoretically as hard or even harder of a problem. With programmatic supervision, you just go back and you change your code like you would with any other type of software, and you iterate until your model is performing up to some quality bar. So to facilitate that, we have tooling for analysis and monitoring. And this allows, again, both iterative improvement, but also adaptation to things changing on the input and on the output side. Here, I'll just briefly note that, again, in multiple settings here, some anonymous customer case studies, also some published peer-reviewed case studies with Intel, Stanford, the use case I'm referencing there, as well as others, Google, where we saved, or rather this Snorkel flow approach saved person months to even person years of manual labeling time by switching to this programmatic development approach, which instead took on the order of hours or a couple of days. And so again, just to wrap up this little part, this idea, in a nutshell, is you can actually involve subject matter experts directly in the development process, move beyond this kind of manual hand labeling process, and not just move forward in terms of speed, but also in adaptability, auditability, modularity, performance. Okay, so let me pause there and just see if there are any questions on this kind of, workflow. And again, I'm sharing it not just to talk specifically about this Snorkel flow system, but also about this, one example of a data-centric AI development system, where again, what's meant by that is not that you don't develop the model or iterate on it somewhat, but that the center of the iteration process, the center of the development process, is about developing and manipulating and managing the data, the training data. Let me pause and see if there are questions here. Otherwise, I'm going to go into some other topics of recent interest. Just as a quick preview, I'll talk a little bit about leveraging ontologies and structured knowledge as a form of weak supervision. I'll talk a little bit about some of the work myself and in particular colleagues have done on applying these techniques to image and other data modalities. And if we have time, I could talk briefly. I know we're running out of time, but I could talk briefly on other operators. But any questions on this basic idea of programmatic supervision in this Snorkel way? Cool. Okay. So I'm gonna. Oh, sorry. Someone was gonna say something.
It's okay.
Okay, cool. So I'm just gonna go through, and please interrupt me. I'm gonna just kind of give a little bit of a whirlwind tour of some other topics that are, potentially of interest in the last 10 minutes here. And if anyone has, comments or questions, please just jump in, and I'll pause. So one cool idea that there's been some recent, both practical as well as academic work around is this idea of using this idea of programmatic or weak supervision to form effectively a bridge between, structured expert knowledge, often in the form of things like ontologies or knowledge bases, or maybe, rule-based systems like the expert systems of, the 80s and et cetera. Use this as a way to create labeling functions, programmatically label data, and train machine learning models. So effectively, leverage all of this knowledge we have, which often is, very rich in information, very precise, but fails to cover and generalize to the long tail of data patterns, especially unstructured data patterns that are out there. But use this to bootstrap or train a machine learning model that is quite good at generalizing to these diverse patterns, and do so through that same programmatic supervision paradigm. One area where, again, both practical work in the Snorkel platform as well as academic side work a lot around some medical tasks is, I'll just paint the very basic idea, which is you can take these ontologies. Let's take an example from my colleague Jason Fries at Stanford, working on biomedical entity tagging. There was a 2020 paper around this, around some recent work here, as well as a bunch of other stuff. Basic idea is you have all of these medical ontologies that have all of these, phrases and keywords for different, things that you want to tag in, say, an electronic health record. What you can do is you can automatically slice up those ontologies, those effectively hierarchies or DAGs or trees of these patterns, and use them to create labeling functions, and then feed those into a system like Snorkel and use that to label data, train models. And effectively what you're doing here in a nutshell is you're learning to weight and combine different components of potentially multiple ontologies as a way of labeling some data to train a model that can then generalize beyond what the ontology covers. So maybe your ontology includes, the word, to keep it really simple, disease, but not synonyms of disease. You can get that word from the ontology, reweight it with maybe other conflicting signals from other ontologies, and then train a model that, whether through pre-training or just training over lots of unlabeled data, can learn to generalize to, say, synonyms of the word disease. All right, so that's you're bridging this great source of codified expert knowledge with the generalization capabilities of modern machine learning. So that's just a high-level idea. I'll also just give a little bit of a high-level overview of how this paradigm translates to image and video and other modalities, where there's a lot of, again, both real-world deployed, but also research work going on still. And some of this work has been done in collaboration with a lot of great partners. I'll just present a couple of high-level ideas of how this is done. So one idea is writing these labeling functions over pre-processed primitives in more complex data modalities like images. So you might imagine, like some of the examples I gave, that you could write a labeling function over something like text by saying, look for these keywords, for example. But how do you do that over something like an image, or even a more complex modality where you just have raw pixels? Well, one idea is, and this has been the subject of some machine learning and also applied papers. One of the first ones from my colleague Paroma was in NeurIPS in 2017, also a Nature Communications paper, 2019 around a medical use case, and a bunch of other work since then. Let's take a really simple example. Let's say you want to classify or you want to label some data to train a model to classify whether someone is riding a bike or not. Again, be really tricky to figure out how you would write a function or heuristic to give any signal here. But one of the really interesting and useful things out in the world is that there's tons of ways to, for example, put bounding boxes, somewhat noisily, but that's fine given our paradigm, around people and bicycles, for example. So what you can do is you can take one or potentially more off-the-shelf, let's say, bounding box detectors or feature extractors, pre-populate the image with that, and then let people write labeling functions over those boxes. So for example, look for a person and bike bounding box that are aligned and have the right, perspective alignment and positioning. Right, so basically, give users these building blocks, which themselves might be sources of noise or error, which also may induce correlations because different labeling functions that utilize the same building blocks or primitives are then going to be correlated in odd ways or potentially difficult ways. But we can tackle that problem using, again, theoretically backed modeling techniques and use that to, again, very practically and programmatically supervise machine learning models. Other examples of this paradigm include, it's not just bounding boxes. You could think of features. We did a use case with mammography where you ask the doctors to, write labeling functions over features like area of bright spots or edges or other artifacts that we could automatically extract. So again, general theme here is use commodity, potentially noisy techniques to extract features or building blocks out of a complex modality like image, and then let people write programmatic supervision over those building blocks. And there's been a bunch of extensions to video and all kinds of other stuff in recent publications that I'll skip over for time. Self-driving, video, cardiac monitoring, all kinds of great examples of this out there. Okay, so that was one idea. Another idea is one of using what we call cross-modal supervision, which in some senses is a kind of simple trick, but it's also a very powerful and ubiquitous one we found in practice. So the high level idea here, and this actually was how we did the radiology example that I referenced at the beginning of the talk. So I'll reference back to that. The basic idea is that you might have two data modalities or two feature sets present at training time, but not at inference or testing or deployment time. So let me illustrate with an example. Imagine, and this is actually the case for that initial example I led with, you have chest x-rays, which are images. You also have unstructured text reports of, from the doctor or the nurse. So you don't have the labels that we want, but you do have text data as well as the image data. What you can do is you can write weak supervision, like labeling functions, over the text. You could train a model that just takes in the images, and then at production time, when you don't have the text reports because the image just came in to the hospital queue, you can't apply the labeling functions. And this is actually another answer to the great question that was asked early on in the talk. But you have a model that has been trained on that weak supervision that can take in images and perform inferences over them. So effectively, you're using this training data as a way of transferring domain knowledge from one modality or feature set to another. Other examples, including in a paper we published with Google, include, instead of having text and image, maybe having what we call non-servable features, like historical data or private data, or very slow computationally taxing data that can be used to train a model, but are not usable in production under production SLAs. Use those to train a model that is operating over those servable or production-ready features. And that's this example. I'm going to skip by this. And then I'll just briefly mention one last bit here, and then I'll wrap up, which is that a third idea of how to handle things, this goes for text as well, but especially for these more complex modalities like image, video, et cetera, is to use other operators beyond just labeling. And in particular, a bunch of our work is focused on 3 of these operators, and there's still a lot of ongoing and exciting work around these. Labeling we talked about. Another one is transformation or augmenting of data. The canonical example here is I'll go through this in a second, and also slicing or partitioning data. Transforming data, the canonical example is if you look in most image classification pipelines, for example, you'll note that there's some pre-processing step, usually done ad hoc, where you're doing things like stretching, rotating, blurring the images. You're effectively creating all these perturbed copies of the data to teach the model to ignore those perturbations. And actually, the presence of data augmentation and how you do the data augmentation, again, just like labeling, can have a much, much larger effect on the model performance than compared to the choice of model architecture. And so we've done some work, and now there's a bunch of other work that's followed this of learning how to take in basic, what we call transformation functions from users about basic augmentation operations. Things like rotations, we know that shouldn't affect the classifier, so let's put that in, and figuring out how to automatically combine and optimize them. And that's just one. Obviously, there are others and others beyond this list as well. So we've done some work on what we call slicing or partitioning of data, where the idea is to not just label or augment data homogeneously across the full data set, but to also identify subsets or slices of data that are really important for the model to get right, because maybe they're very difficult or very critical to performance. And this is another way in which you're effectively programming your model by manipulating and developing your data. So these are all examples of this kind of data-centric focus where you're enacting programmatic operations over your data to develop your models. And I am very certain there are many more out there, but these are some of the ones that we've tackled. Anyway, I know I'm at time, so I'm going to pause there. And if I have a minute or two, I'm happy to take any last questions. Otherwise, happy to wrap up. Yes, any questions?
高島さんお願いします。
すいません。他の人が話してると思いました。Hi, Alex. Thank you so much for the talk. I'm at Carnegie Mellon, so on the US side of things.
Oh, awesome.
So a question about detecting, say, collusion. So you said assuming sufficient, sufficient lack of collusion, you can get very good formal guarantees. But in practice, collusion may not be obvious, right? So for example, if my startup buddies, we all write labeling functions, obviously there's going to be some bias with regard to the fact that we belong to a similar group, we talk to each other, we go to lunch together. How do you detect collusion in practice? That's not really collusion adversarially, but it's collusion there in terms of data.
Yeah, and usually usually how we phrase it is just correlation. I was saying collusion in my example, but usually it's about correlations, and really what you're trying to prevent, to your point, is you don't want to double count the data, for example, right? Imagine I have one labeling function that says look for the prefix pneumo in the chest X-ray readout, and another one that says look for pneumothorax, right? There's a clear logical subsumption relationship there that will happen even more when you're writing functions versus when you're thinking about, say, crowd workers, for example, right? So this takes me to the broader point that is important to make. Again, I know you know this already and everyone knows this, but it's worth emphasizing as a framing point is that, all models are going to be wrong. It's just about, what's the best way to make them, less wrong, right? What should you prioritize trying to model specifically? And so the weak supervision models that we train, they're obviously oversimplified views of the world. The question is just what should we try to actually model and learn? And so we start with modeling, global accuracies. And then what we've done in other work is modeling other things like correlations or collusions, or bias areas where they're better or worse differentially based on features, things like this. Now, how do we do that? We leverage a lot of the same kind of modeling and theoretical apparatus. And so again, the intuition is just like by looking at, say, the covariance matrix, you can see that, labeling function number 1 is usually in the majority, so we trust it more. You can see that, the pair, maybe you and your friends' labeling functions tend to agree in a way that suggests they're not conditionally independent, meaning even conditioned on the true unobserved latent variable, latent ground truth label, they're voting the same way more than you'd expect if they were independent conditioned on the ground truth, which is the usual kind of, conditional independence assumption that you make in this space. And so again, it just relies on the same basic, the same basic theory of observe lots of agreement and disagreement patterns to detect not just accuracy, but also correlations. Now, what we do in practice is we generally split this up into, or in some work, the one with the big, at least with the formal guarantees, we split it up into a two-step process, which is very standard with probabilistic graphical modeling in general, which is first we do structure learning, which is essentially trying to model which correlations are even worth modeling. And then we do the learning, which is now learning the weights of the correlations along with the accuracies. So that first step is saying, okay, ideally, we'd say, okay, look, you and your friends, all of those labeling functions should have pairwise correlations because there's too much agreement there. And we'll model those as edges. And then we'll separately then run the same learning process to learn how much to weight those edges. Yeah, and then as to the kind of assumption of at least three clusters of labeling functions that you can at least model as conditionally independent. That goes back to very kind of fundamental theoretical constraints. You need at least kind of 3 independent sources, right? So you can think about the intuition, at least that I fall back to, is you need at minimum, a tiebreaker. You need 2 people and then a tiebreaker to ever theoretically break fundamental symmetries. But it kind of comes back to that, and so that's the bare minimum you need.
In practice, do you get 3? Or at least 3?
Yeah, in practice, a lot of this is just, in practice, and this is why I led with some of the practical things, because that's where my head's been at the last year or two, especially, or some of it, is a lot of what we try to do is we try to build these interfaces to make it as fast and easy as possible for subject matter experts, especially, to just dump in lots of these labeling functions, right? And then, what we're trying to do is make sure that there aren't kind of, big clusters of double counting or of low quality ones that distort the result. So in practice, we usually have dozens, and it's done very iteratively. So actually, if we tell someone, hey, we think there's too many correlations detected, this can then be given as a feedback in the iterative development loop.
I see. So I guess you're able to detect it before it even deploys, which would be nice if you got autonomous cars. You don't want that deploying, right? So.
Yeah. And again, that's also a benefit of this kind of 2-step process breakdown, which actually is very standard in the PGM literature, but we had adopted here as well, where you do structure learning first, and often in a more cheap way. You can say, okay, we think there's too much density of correlations here. You better introduce some more independent signal into the problem, even before running the rest of the process.
I see. Yeah, maybe even like higher.
Sorry, but time is over.
Oh, sorry about that. Okay, yeah. Anyway, thank you for the great question, and thank you everyone for the time.
So can we finish, Alex?
Yes. Yeah. I'm sorry for going over, and thank you again, everyone, so much for the time and the great questions.
Yeah, thank you very much.